Welcome back. Today we start moving into the realm of our preparations, laying the foundations for AC, understanding AC circuits. And to do that, we have to learn something about the right triangle. The right triangle is the foundation for understanding something called phasors and vectors. So in order for us to do the real imaginary analysis that we talked about, we have to understand how to operate on and manipulate a right triangle so that we get the understanding of sides and angles that relate to vector lengths and angle relationships. So we're going to start off understanding a little bit about the sides and the angles. How do we determine them? How do we recognize which side and angles correspond? And then look at the Pythagorean theorem, an algebraic approach to calculating the sides of a triangle. And then we get back in specifically into the trigonometric functions, some outdated technology, the trigonometric tables, but it's worth looking at them and understanding them. Understanding inverse trigonometric functions because they help us knowing one thing like an angle determine the sides, and then setting up trigonometric equations. So all of these are part of our objectives in this chapter to understand the right triangle and trigonometric functions. So we'll be focusing on the right triangle. The right triangle as a trigonometric tool for performing circuit analysis and in some of your other classes like physics doing vector analysis. The right triangle is easily discernible because only one side forms a 90-degree angle. So all of the other obtuse, isosceles, and other designations of triangles do not have that one side 90-degree angle. So if we take a look at this, you can see that the angle A and angle B must sum to equal 90 degrees. The total of the triangle has a total of 180 degrees then. Side C is always the hypotenuse, the long side. This is the side we'll be most interested in because it's the hypotenuse, or side C, that forms the vector or the phasor that we're going to be interested in later. The other two sides, the opposite and the adjacent, are formed, and the relationship between them, as it shows here, the hypotenuse is opposite angle C. The adjacent is opposite, in this case, angle B, and opposite is across from angle A. So you have to learn how to navigate around the right triangle so that you're looking at the right angle and the right side when you're doing your calculations. When discussing angle A, side B is the adjacent side, the side next to angle A, and side A is the opposite side. When discussing angle B, side A is the adjacent side, and side B is the side opposite. C is always the hypotenuse. So you always have to be careful when you're looking at the angles and the sides. In this case, side B is opposite angle B. Side A is opposite angle A. Okay, so you'll get used to that as you start doing the problems. Not all triangles are labeled as previously illustrated. Here you can see very simply we have them labeled ABC. But when we start doing applications, the angles and sides become very specifically labeled. The sides and the angles are annotated then according to their application. The angle theta and phi are common angle notations in engineering applications and analysis. You should be able to identify the relationships among the sides and angles regardless of the positions of the triangle. So here we have just some examples here where we place some angles. Here you can see theta and phi. This is your typical setup for an application using conductance and susceptance and admittance. So another tool is the use of the Pythagorean theorem. The Pythagorean theorem states in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. You probably remember that from the Scarecrow in The Wizard of Oz. That's his aha moment. So the Pythagorean theorem, c squared is equal to a squared plus b squared, which we can manipulate by taking the square root of both sides and say that the hypotenuse then is equal to the square root of the sum of the squares a and b of those sides. If the two sides of a right triangle are known, then the third side can be found using the Pythagorean theorem. Suppose, though, sides a and b are length 6 and 8. Okay, so here's an example. What's the length of the hypotenuse? So since we have it already set up that we can solve for c by using the manipulated form c is equal to the square root of a squared plus b squared, it's simply a matter of placing a and c into the relationships, square them, sum them, take the square root, and we can see that the hypotenuse in this case is a length of 10. In this example, there are no units. Always be careful to maintain your units. Suppose the lengths of the sides are 5 and 8 respectively, and we want to calculate b. Well, this requires us to move some terms around to simplify the expression before we start solving. So we start with the basic equation. C squared is equal to a squared plus b squared. Let's move b squared to one side, so we're going to subtract a squared from the other side. Take the square root of both sides, and then just start plugging in our values. 8 and 5 squared, 64 minus 25, we end up with 39 now, or the side C equaling 6.24. Another example, some larger numbers. Suppose that sides B and C are of the length 75 and 150. So now we're going to solve for A instead of B. So we're going to isolate A to the left side of the equation, B to the right side of the equation. Again, it's set up exactly the same way. A is equal to the square root of C squared minus B squared. Plug in your values. 150 squared minus 75 squared gives us 16,875. Take the square root. We get the length of side C as 130. So using the Pythagorean theorem is great if we only want to solve for the sides of the triangle. There is no calculation ability to come up with the angles. That requires a different set of rules. Let's look at an AC application. In an AC application, the sides of the triangle could represent a circuit resistance. Oh, why that did that? Let's put it back to what it's supposed to be. R. A reactance and an impedance Z, whose unit of measure is the ohm. So Z in this case becomes the hypotenuse. It's in right triangle analysis, that is the resultant, or sometimes called the equilibrium. So the expression now becomes Z squared equals R squared plus X squared. Same process though. Okay, we've got Z squared equals R squared plus X squared. We want to solve for X squared. In this case, they asked us to find the reactance. So we're going to solve for the reactance here. X is equal to the impedance squared minus the resistance squared. Take the square root, and we end up with 42.1 K ohms as our reactance. Now, the other part of the equation says which of the angles is greater, theta or phi. To do that, this actually takes a skip forward. I'm surprised that they did it this way. But we can take the length of the two sides, X and Z, as the ratio to give us our sine. So the sine of the angle, which we don't know at this point, theta, is 0.5. If I take something called the inverse sine, which we're going to look at more in depth later on, if I take the inverse sine of 0.5, then it tells me it's 31 degrees. Do the same thing for angle phi by using the ratio of r to z. I come up with 0.85, and the inverse sine becomes an angle of 58. Okay, so this is how we solve for those values associated with the Pythagorean theorem. In this case, we're going to do the same thing with an example of susceptance, admittance, and conductance. Follows the exact same path here. You can see, just using Pythagorean theorem, we end up with Y, the admittance of 721 microsiemens. Okay, so another example here. Again, the thing is don't be intimidated by the variables that we use, because they're going to change to fit your specific needs and your application. Okay, so we're going to stop with that. When we come back, we're going to look at the trigonometric functions.